Hello everyone, and welcome to this presentation on the amazing thoughts about the Fibonacci sequence. Today, we are going to explore one of the most fascinating mathematical patterns found throughout nature, the Fibonacci sequence and the golden ratio. Nature has its own language, and that language is mathematics. From the tiniest flower petals to the largest galaxies, the Fibonacci pattern appeared everywhere. Let's discover together how mathematics and nature are beautifully connected. What is the Fibonacci sequence? The Fibonacci sequence begins with 0 and 1. Each subsequent number is the sum of two numbers before it. So we have 1, 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and 144, and so on. This simple rule, adding the previous two numbers, creates a sequence that appears everywhere in the nature. And the beauty of it is that this simple pattern leads to some truly extraordinary mathematical properties. Here you can see that the answer fn equals to fn minus 1 plus fn minus 2 for n greater than or equal to 2. And for first and second term, f0 is 0 and f1 is 1. This is the definition of the Fibonacci sequence. So, first, we investigate the first property, the magic, called Fibonacci identity. Fn to the 2 equals to Fn minus 1 multiply Fn plus 1 plus or minus 1. Examples with F5 to the 2 is equal to the 5 to the 2 equals to 25. And F4 multiply F6 equals to 3 multiply 8 equals to 24. Then 25 equals to 24 plus 1. All for 6 terms. F6 to the 2 equals to 8 to the 2 equals to 64. And F5 multiply F7 equals to 5 multiply 13 equals to 65. And we know that the 64 equals to 65 minus 1. The identity holds for all Fibonacci numbers. And also, another property is the sum of Fibonacci numbers. Sum of odd index Fibonacci numbers, f1 plus f3 plus f5, and so on plus f2n minus 1 equal to f2n. For example, here, f1 plus f3 plus f5 plus f7 equals to 1 plus 2 plus 5 plus 13 equals to 21. 21 is 8th term of the Fibonacci sequence equals to f8. And sum of square of Fibonacci number, f1 to the 2 plus f2 to the 2 plus fn to the 2 equals to sn multiply fn plus 1. Also, here we have an example. 1 to the 2 plus 1 to the 2, the second sentences. 2 to the 2 and plus 5 to the 2 equals to 1 plus 1 plus 5, 4 plus 9 plus 25 equals to 40 equals to 5 multiply 8. And also, it has some relation with the prime numbers. Interesting relation. If n is prime, then fn necessarily primes. And here we can see also some examples. N is 3's prime number, then fn 2, then plus is prime. N is 5, then fn is 5. N is 7, then 7 is prime number, then fn is 13, 13 is prime number. And also for fn equals to 11, then fn is 89. N equals to 13, fn equals to 233. All the fn and all these prime. Also here you can see an important note. The converse is not always true, because here f4 is 3 3 is prime, but 4 is not prime. So this is one side, not the both side. Also, with that, we know that there is a deep connection between Fibonacci and prime numbers. Here is a small part of that connection. Also, Fibonacci and continued fraction. Here is 5. 5 equals to 1 plus this continued fraction. 1 plus 1 over 1 plus 1 over, and so on. If we calculate the sum of two sentences, it equal to 1 plus 1 over 1 equals to 1 plus 1 equals to 2. So for this second sum of two sentences is equal to 2. Relation to first sentence equal to 2 over 1 equals to 2. Let's say the summation of three sentences equals to 1 plus 1 over 1 plus 1 over 1 equals to 3 to the 2 equals to 1.5. For the summation of three sentences of the continued above continued fraction is 5 over 3. 5 over 3 approximately is 1.665. And so on for the four sentences, 8 over 5 is equals to 1.6. For the summation of 5 terms equals to 13 over 8 equals to 1.625. And finally, for the sixth term, the summation of each term of the continued fraction is equal to 21 over 13, approximately equal to 1.615. Is close to the issue. So for the continuing fraction, the ratio of the constant Fibonacci numbers converges to the 5. So fn plus 1 over fn goes to 5 equals to approximately equals to 5.818. So also in this application of the Fibonacci numbering, we'll let this in the continued fractions. And finally, for the composite number, if n is composite, then fn is composite. Here we have some composite number, and for 6, 8, 9, and 10. Then fn for n equals to 3, fn is 3, is prime. But for 6, n is 6, fn is 8. For n, 8, fn is 21. For 9, fn is 34. And for n equals to 10, fn is 65. So, idempotent theorem can be defined. If m divides n, then fm divides fn. This is related to the Fibonacci sequences. Fascinating divisibility property of the Fibonacci. And also it had some application in the nature and art. We investigate this application in the separate video in future. In the nature, number of flower petals 3, 5, 8, 13, 21, sunflower spiral pattern. Not ritual astral 3 branching pattern, pineapple stairs, and also in art and architecture. Golden ratio in the Da Vinci paintings, you can see that the golden ratio in the painting of Leonardo da Vinci. Ancient Greek architecture, in Parthenon also, it has appeared in the Parthenon. A logo and blind design, some famous companies use the golden ratio in their design of logos. And although for the photography, the golden ratio also can be found. So we can tell mathematics at the heart of the nature and art. All here you can see the summary of an amazing Fibonacci property. So that fn2 equals to fn minus 1 multiply fn plus 1 plus minus 1. Or sum up odds 10 of the Fibonacci. f1 plus f3 plus f2n minus 1 equal to f2n. And sum up the squares fn2 to the 2f to the 2 and fn to the 2 equal to sn multiply fn plus 1. And although it has some connection with prime numbers and with the continuing fraction, and also the divisibility property of the Fibonacci sequence. Fibonacci, and finally, so the Fibonacci is one of the most widely used sequential mathematics with amazing properties that are still being discovered today. Thanks for watching. See you later.